Okay, so welcome back. Now I'm going to start my lectures on chapter 22. I've got a lot of good demos and stuff that I've done on 22 on thermodynamics engines, but now I'm going to actually formally start chapter 22 lectures. On section 1 and section 2 we talk about heat engines and the second law of thermodynamics. And then in section 2, we apply that to heat pumps and refrigerators and the second law of thermodynamics. So we draw a basic format for a heat engine. We have a heat reservoir. Okay, so basically a heat engine is using some kind of source, a source of heat. And usually we use a heat reservoir for that, and then we are able to extract some kind of heat from that. We call that Q hot, and then we draw the engine like this. Then we have some kind of mechanism, an engine that is able to extract that heat and do usable work with that. So we have a work output, work out. So in the case of a car, we're able to drive the car, but then we cannot completely do work without dumping some heat to the environment, or we call that the cold reservoir. So it has to be some kind of a reservoir that we're dumping heat to. So we call that the cold environment, cold reservoir, and then we dump heat Q cold. Okay, so therefore the heat that we extract, Q heat, is equal to work out, the work that the engine does, plus the Q cold. Okay, the efficiency of the heat engine is defined as 100% times how much work that the engine did, divided by the Q hot. In other words, how much work were you able to get out of that engine divided by how much heat it took to do that work, right? So now, if Q cold could be made to be zero, if Q cold is zero, right, that means you don't dump any heat to the cold reservoir. What would the efficiency of the engine be? Well, if Q cold was zero, then Q hot would be equal to work out. So this and this would equal, and then you would have a 100% efficient engine, right? If Q cold was zero. Well, this is where the Kelvin-Planck form of the second law comes in, the Kelvin-Planck form. The Kelvin-Planck form is you can never have an engine that operates between two reservoirs that is 100% efficient, right? Extract heat and completely do work without dumping some heat out. So that would be 100% efficient. Second law of thermodynamics prevents that from happening. Remember, second law of thermodynamics is also the law that says the entropy of the universe always increases over time, the disorder. But the other way to say it is that you can't have 100% efficient, always running engines that perform work. For every 1 joule of heat that they extract, they perform 1 joule of work, right? So you can't have that. Now the equation that I have for heat, I can also make it a power equation. I can divide this by time. Then I can say the power that you extract, in other words, how many joules per second you extract from the heat reservoir, is equal to the work out over work over time is going to be power out plus the power cold. So basically this is how many joules of heat you're extracting from the hot reservoir per second. So this is measured in watts. This is how much work you are doing per second, so that would be also watts. And then this is how much you're dumping watts. So let's say the car is a certain rating of horsepower, right? We can change that horsepower rating to watts, and that would be the work out of the car. But then it would take a lot of power to extract from the gasoline per unit time. And then you would also be extracting and dumping a lot of power to the environment, right, in watts. So you always have to dump some out, okay? So now we could also write this way. Okay, so we could say efficiency is 100% times, okay, work out is equal to Q hot minus Q cold over Q hot, right? Since work out was the difference of Q hot and Q cold. Then I can divide the Q hot into it, 100% times 1 minus Q cold over Q hot. This is another way to express the efficiency of an engine. Now in section 4, when we talk about the Carnot cycle, we're going to prove a particular equation, the efficiency of a Carnot cycle. The Carnot cycle is going to be the most efficient cycle that can run between two reservoirs, between two heat reservoirs. It's the most efficient. So it can be shown that the most efficient an engine running between two reservoirs, which is the Carnot cycle, has an efficiency equal to 1 minus T cold over T hot. This is a general equation that would be true even if an engine is not utilizing the Carnot cycle. It would also always be 1 minus Q cold over Q hot. But for those engines that are utilizing the Carnot cycle, they are the most efficient engines that can run, and this is their highest efficiency. 1 minus T cold over T hot. So you basically replace the Q cold by T cold and the Q hot by the T hot. Then you get the efficiency, the Carnot efficiency. So this is chapter 22, section 4, that they talk about that. Okay, in section 2 of chapter 22, we talk about heat pumps and refrigerators. So the heat pumps are like the heaters that we use in the winter times, right? And then the refrigerators are the ones that we have in our kitchens, right? Okay, so then this is how we draw the heat pumps. We have here a heat pump. And then we put in work in. So instead of work out as for a heat engine, which was performing work, this one we have to put in the work, right? And then into the heat pump. And then the heat pump is gonna be able to extract heat from a cold reservoir. This is a cold reservoir. It extracts heat from a cold reservoir, so we call it Q cold, and then it dumps that heat into the hot reservoir. So this is going to be the hot reservoir. Okay, so in this case, what's going to be the cold reservoir? What's the hot reservoir? The hot reservoir is going to be the inside of your house on a cold winter day. So the inside of house. Okay, cold reservoir is going to be the outside cold weather, which is already cold. So cold outside. Okay, the cold outside. So here's what you're doing. You're taking heat from the outside cold air, which is already cold, but you're taking heat how? By doing work into the heat pump. Okay, you're extracting heat from the outside cold, which is making the outside cold even colder, but not really that much colder because you can't affect the outside atmosphere that much. It's really huge. So by extracting heat from it, you're not really making that much colder. But then you're able to dump heat into the hot reservoir inside so that the inside hot stays hot. So you're supplying heat to the hot reservoir, because otherwise if you don't do that, the heat from the inside is going to go to the outside, and then the inside is going to be just as cold as the outside. So you don't want the inside of the house to be cold on a cold winter day, right? So you're dumping heat into the inside of the house, which is already hot, to keep it hot, right? So then, so how is the equation here? We can say work in plus Q cold is equal to Q hot. So the amount that you can dump into the hot reservoir is equal to the sum of how much work you put in plus how much heat you extracted from the cold reservoir, right? And for the heat pumps, we define something known as the coefficient of power. Coefficient of power for a heat pump is going to be defined as Q hot over work in. This is definition. Now what's the logic of that? Remember, for heat engines, we define them this way. Efficiency, we define them as 100% times work out over Q hot. Okay, so the efficiency of an engine cannot be any larger than 100%. So that's the maximum. But as I said, the Carnot efficiency is the actual theoretical maximum that an engine can be no more than 100%, no more than the Carnot efficiency, which might be like 50, 60% depending on the cycle that you're using, right? But the theoretical maximum efficiency, you can never have an efficiency larger than 1. Remember that you cannot have Q cold 0, so efficiency can always has to be less than 1. Now the coefficient of power, they defined it opposite. The work was in the denominator, the Q hot was in the numerator. What's the logic of that? So here's what it's doing. It's dividing in the numerator, it's putting what is the goal of that machine. The goal of that machine is not to do work. The goal of that machine is to dump heat inside of your room, right? The goal of an engine is to do work. Now, how much heat did it take to do that work? This is the Q hot. That's how much heat you had to extract from the hot reservoir, right, in order to be able to do that work, right? Now, the coefficient of power, it's how much heat you're able to dump into the hot reservoir. The goal of the heat pump is to dump heat to the hot reservoir. So it's taking your goal and then dividing it by how much work it took to accomplish that goal. Okay, so what's going to happen? Well, work in is equal to Q hot minus Q cold, right, from this equation. Okay, so then what's going to happen? Coefficient of power, heat pump. One of the things we can see is that the Q hot is always larger than work in, right? Because it's the sum of Q cold and work in. So if this number is larger than this, that means coefficient of power is always larger than 1, instead of being always less than 1, you see? So it's always larger or equal to 1. Now, can it ever equal 1? What would have to happen if it's equal to 1? Now, we could rewrite this way. We could take the Q hot, bring it to the denominator, and then divide Q hot into each of this. Then we can say 1 minus Q cold over Q hot. We can say this is greater or same as 1. So this is just different ways of writing them. 1 over 1 minus Q cold over Q hot, or we can write them as Q hot over Q hot minus Q cold, or we can write them this way, Q hot over work in. Okay? So what would it take for the coefficient of power to be 1? Okay, well, if Q cold is 0, okay, then what would happen? Q cold was 0, this would cancel this, and you would have a coefficient of power of 1. So now, what is our desire? Our desire is for the coefficient of power to be as high as possible. Here, the efficiency, we also want it to be as high as possible because we want it to be able to do as much work as possible. But its limitation is that we can't do more work than this workout can never be larger than Q hot, so we can't have more than 100%. We can never have an efficiency more than 1. Okay, here, can we ever have that? Well, actually, this is always going to be greater or the same as 1. The best possible engine, if it could possibly exist, is that work in is 0, right? If we don't even have to do any work, this would disappear. I would just extract heat from a cold reservoir and I would all dump that all in without having to do work in, right? So if work in was 0, what would happen? Okay? The limit of this function as this approaches 0 is infinity. So the coefficient of power would reach infinity. And this is not allowed, right? Just like it's not allowed for an engine to be 100% efficient, this one is also not allowed. So the Clausius form of the second law of thermodynamics says that heat pump or refrigerator cannot function by simply extracting heat from a cold reservoir and dumping heat to a hot reservoir without the input of work. So that means work in cannot be equal to 0. Okay? This is called the Clausius form. Clausius form of second law. Okay? So that means the coefficient of power cannot be infinite. But if we can't be infinite, can we approach a large number? Okay? Ideally, we could have coefficient of power is equal to 4 or 5 or 6, right? So what would that mean? The higher it is, the better that is. If the coefficient of power is 5, right, what would that mean? That would mean Q hot is equal to 5 times the work in, right? So if that's true, work in plus Q cold is equal to 5 times, and then I'm putting here Q hot is equal to 5 work in, right? And then we get here Q cold is equal to 4 work in, and then work in is equal to a quarter Q cold. Okay? And then what would Q hot be? Since Q hot is equal to 5 work in, so that's going to be 5/4 Q cold. Okay? So in other words, let's just say that Q cold was equal to 100 joules, right? And then in this case, what would Q hot be? Q hot would be 5/4 of 100, so that would be 125 joules. And then work in would be quarter of 100, would be 25 joules. Okay? So if you had the engine, if you had the heat pump like this, if it only took you 25 joules to extract 100 joules from a cold reservoir and to dump 125 joules to a hot reservoir, right? This is your inside of your house. What would the coefficient of power there be? Coefficient of power is equal to 125 over 25. 125 over 25, so that would be 5. So that would be a really good heat pump. It's only taking you 25 joules of work, right, in order to dump 125 joules into the hot reservoir, okay? But now, what if this one was 50 joules? What would happen? 50 joules, this one would have to be what? So it's taking 50 joules of work, but then this would be 75, right? 50 plus 75 is 125. Now what's the coefficient of power? Now 125 divided by 50, coefficient of power 125 divided by 50, so that's going to be 2, right? And then 2.5. So the coefficient of power went down. This engine, this heat pump is not as good because it's taking 50 joules of work to extract 75 joules here, and then in order to dump 125. So right now, forget that the extraction amount. The focus on this. A minute ago it was 125 and 25, so that was a ratio of 5. Now it's 125, 50. So you're doing 50 joules of work, it's taking more work. That means that heat pump is not as efficient. That means its coefficient of power drops from 5 to 2.5, right? So then if it took, let's say, 100 joules of work, and this would be 25. So then the coefficient of power would be what? 125 over 100, 1.25. That means the heat pump is doing most of the work. The outside air, the outside cold air is not really contributing much, you see? It's only giving you 25 joules of energy. But you have to put in 100 joules of work. So you see why? As the coefficient of power drops, the heat pump is not really good at all, right? Now, could you have this? 0 and 125. In order to dump 125 joules of heat to the hot reservoir, you have to do 125 joules of work. Well, that's possible, but that's not really a good heat pump. You're not using the cold reservoir at all. So coefficient of power will just be 1. Is that theoretically possible? Yeah, but who would design a heat pump like that? It's just not worth it, right? So theoretically, you can have COP equal 1, but you can't have efficiency of a heat engine being 1, right? But you could have COP being 1, but you can never have COP be infinity, okay? So now let's talk about refrigerator. How is a refrigerator different? The equation is the same. So work in plus Q cold is equal to Q hot. But it's kind of reverse. In other words, this is the difference. In the refrigerator, the goal is not to dump heat into your room, but its goal is to extract heat from the cold reservoir, and the cold reservoir is inside of the refrigerator. Inside of refrigerator. And you want to make the cold reservoir even colder. So the goal of the refrigerator is extracting heat from the cold inside of the refrigerator. But by doing that, what is it doing? It's dumping heat, unneeded heat, to the hot reservoir. The hot reservoir is your room, your kitchen, right? So we don't really even care about that, but it's an undesired necessity, right? But it has to dump the heat to your room through the back coils of the refrigerator. So this is basically the hot kitchen, or wherever else you put the refrigerator, right? So you're extracting heat from the cold inside, and that's your goal. So how should we define the COP of the refrigerator? Okay, remember in the numerator, we're gonna put the goal of that machine, that instrument, right? So the goal of it is to extract heat from a cold reservoir. So we're gonna say QC divided by work in. How did we define the heat pump? Q hot divided by work in, right? So here we're gonna define it as QC divided by work in. Now, can the COP ever be infinity? No. Since work in can never be zero, so W can never be zero, that means COP can never be infinity. Right? So same argument as the heat pump. And how can we simplify this equation? How can we rewrite it? We can say Q cold, and then the work in is equal to Q hot minus Q cold. The other equation, we had Q hot up here, but here we have Q cold. And then we can divide here, Q cold goes down to the denominator, we have Q hot over Q cold minus 1. Okay? So it's a little bit different of an expression, because instead of Q hot, you have Q cold on the top. Okay, now let's use the same numbers that we did before. We had a heat pump that had that was dumping 125 joules into the hot reservoir. It was doing 25 joules of work, and then this was 100, right? We noticed that the coefficient of power of this, okay, was equal to 125 over 25, which was 5. Okay, now what if the same apparatus is being used as a refrigerator, which in the real world won't happen like that, but if it was with the same numbers, this is as a heat pump, what would the coefficient of power as a refrigerator be? Then you divide 100 divided by 25, and you get 4, right? So notice that the coefficient of power acting as a refrigerator is less than the coefficient of power as acting as a heat pump, right? By one numerical number, right? So since the Q cold plus the work in has to equal to Q hot, Q cold is always going to be smaller than Q hot, and then when you do the ratio of Q cold to work in, it's always going to be smaller than the ratio of Q hot to work in, you see? So now what if this one was 50? If this is 50, let's keep that at 125, and then what is this going to be? This number is going to be 75, right? So now the coefficient of power as a heat pump, and now the coefficient of power as a refrigerator is going to be what? 75 over 50, right? 75 over 50, which is going to be 1.5. So now notice, if you subtract 5 minus 4, you're going to get 1. If you subtract 2.5 minus 1.5, you're also going to get 1, right? So we're kind of seeing a pattern here. Coefficient of power as the heat pump minus coefficient of power refrigerator is 1. You see? So now let's change it a little bit more. Let's say 100. And then keep this at 25 now. So 100 plus 25, that's going to be 125. So then the coefficient of power heat pump is going to be 125 over 100, which is 1 1/4. Right? So we said that heat pump wasn't good at all. Its coefficient of power can be 1, but that's not good. So as you're going down, it's not a good heat pump at all. So it's 1 1/4. But now, behaving as a refrigerator, what is it? COP refrigerator. Well, now it's going to be 25 over 100. 25 over 100, which is 1/4. Well, that's not good at all. You're doing 100 joules of work, you're only extracting 25. I wouldn't buy that refrigerator at all. I mean, theoretically that's possible, but the coefficient of power of a refrigerator, if it's less than 1, it's no good at all. It's an old refrigerator, dump it, right? So the coefficient of power is 1/4. Now notice, 1 1/4 minus 1/4, it's going to give you 1. So it's always going to be true if the same apparatus runs as a heat engine and a refrigerator, then the difference of them is going to be equal to 1. Okay, so with this now you have a little bit introduction into heat engines, heat pumps, refrigerators, efficiency, coefficient of power. Okay, and then from here on out we'll do some examples. Thank you very much.